All right, so we're going to be working now on Chapter 3. When the ball, it says during the impact, the ball creates a crater that is 1.5 meters deep vertically. So what we have here now is this right here represents the velocity at the point of impact. Now, I got this all from Chapter 2. The final velocity, the net velocity at Chapter 2 is the initial here. So that was 45 meters per second. And then the horizontal is 38.7, and the vertical is negative 23. I'm zooming in now because when I put it back on the table, it'll be kind of small to see. Now, I'm going to write these givens here. So this was 45, which I got from Chapter, I got this from Chapter 2 at the end of it, and now it's the initial for Chapter 3, which was at 30.7 degrees. And this VIY is negative 23, and this is 38.7. Big misconception is to make that equal to 0 and that equal to negative 10. You only do that when it flies freely. Okay. We also know that the vertical distance this way is the dy is equal to negative 1.5 meters. Okay, so let's do the first question, V. Now for V, it says calculate the horizontal displacement at the crater. So, just let me use a different sheet here. So to solve for V, we're going to be solving for dx. Now, if we go back here to our original drawing, we'll be solving for dx here. We have dy, that's equal to negative 1.5 meters, and that's the resultant d. We also forgot to put this down from before. The final velocity at the end is equal to 0. So this ball comes to a complete stop. Now, to solve for the horizontal distance, I don't really have enough this way to solve for it algebraically, but I do have enough this way to use trigonometry. As long as I have an angle and this distance, dy here, it suffice. So for V and W, let's do those together at the same time. V and W, well, W asks you to solve for the actual d net, the resultant d. Now, if I'm going to draw a triangle for my step 2 here that they both can share, a right triangle. The vertical distance will represent that, well, the horizontal distance will represent as dx here. The vertical distance will represent as negative 1.5, and the resultant one, and the angle here should be 30.7. Now, there's a couple of different ways that you can solve for this. I know in your reference table for this test, I haven't given you guys TOA yet. So what I'll do is I'll do W first for those who might not have or feel comfortable using TOA. So you could solve for this d net here, or this resultant d, by doing so. Or in this case, I'll use this equation for step 3. I'll use AY equals RA times sine theta. Now, AY in this case is negative 1.5. Now, to make our lives easier, we're going to make everything an absolute value bracket so that the angles come out positive in the end. So we're going to make that positive 1.5 meters, and this will be our RA, what we're solving for, times sine 30.7 degrees. Step 5, if we do, we'll do 1.5, divide that by sine 30.7, and we get 2.9. Okay. So I'll double check, make sure I got this. Yeah, so we have an answer of our resultant is equal to 2.94 meters. That's this hypotenuse right here now. 2.94 meters. Now, to solve for this here, we can just use a squared plus b squared equals c squared. So I'm going to do a squared plus b squared equals c squared, where a is equal to, we'll say that's the one we're solving for, plus b squared. It's a negative 1.5 meters squared. It's okay if you leave a negative here because you'll square it and become positive anyway. And 2.94 meters squared. That's the hypotenuse. So if we solve that, we get a, which is also equal to dx. And that'll give us an answer of, so we have 1.5 squared, and we're going to do 2.94 squared. Subtract that 2.25 and get the square root. That answer gives an answer of 2.53. So that'd be the horizontal distance. Horizontal displacement is actually 2.53 meters.